Good morning, everyone. Welcome to this new Next Friday talk. Today, the guest is Francesco Pesce, a PhD student here at NextLab in Politecnico di Milano. And the theme of the talk will be about hardware acceleration on FPGAs. So thank you, Francesco, for being here with us.
Thank you for having me. Okay, shall I start then?
Yeah.
Okay. Well, hello, everyone. Today, I'm Francesco Pesce. Today, I will talk about my current research project, which is named Turquoise, and it's a hardware-accelerated architectural simulator for Sparse Algebra DSAs. To introduce myself, I am a PhD student here at NextLab, and I also studied here at Politecnico. Particularly, I did the bachelor here in computer science and engineering and the master's in high-performance computing engineering. And I started my PhD in September of last year, which is also when I became an intern at AMD in research and development. And I finished that recently at the end of February of this year. Now I'm a PhD student here, and my research is focused on FPGA-based and heterogeneous acceleration, specifically for data center workloads. Now, the topic of today's talk is related to sparse linear algebra. And to introduce why this is useful, well, we have many different applicative domains, like the ones that I'm showing here, like networks, sparse machine learning and artificial intelligence, computational fluid dynamics, and weather simulations. And in all of these applicative domains, there is a heavy use of a computational domain, which is that of sparse linear algebra. Another thing that we have to take into consideration is that for the last decades, CPUs have consistently been unable to meet the performance and energy efficiency requirement that we need in modern workloads. And in fact, decades ago, we used to have Moore's law, which predicted exponential scaling of CPU performance, and also Dennett scaling, which stated that the energy efficiency would not increase even though the performance did. However, this is no longer the case, and we now have to rely on other ways, such as hardware acceleration, to obtain significant performance. And in fact, there has been a paradigm shift from these traditional architectures, such as CPUs, to domain-specific architectures for DSAs, which are architectures that are tailored to a specific function or set of functions, and in those fields can obtain much higher performance or energy efficiency at the cost of generality. And we also see that, according to the International Energy Association, in 2022, data centers, artificial intelligence, and cryptocurrencies were already consuming 2% of the global electricity. Now it's 2026, so the next report should be out soon. And we expect that this quantity will have increased to 4 to 6% of the total energy expenditure. While we said that domain-specific architectures can have a higher performance and energy efficiency, actually designing these architectures is complex, and it's particularly complex in the case of sparse linear algebra. And this is because sparse algebra workloads are usually irregular, which means that one architecture may not perform at its best on all of the possible inputs that have to be provided to it. And also, sparse algebra DSAs have a very complex design space because, for example, for sparse matrix multiplication, we have many trade-offs that we have to consider, such as the choice of the iteration order, which could be the inner product, the outer product, or the Gustafson product, the choice of the format for the involved tensors, which could be CSR, coordinate, etc. And also the other more fine-grained options, such as the number of processing elements of the architecture in the case of a spatial accelerator, or the size and policy of the cache. And because of this, architectural designers need to rely on simulators to make their design space exploration simpler and faster. Traditionally, we had cycle-level simulators to simulate architectures, and these still exist and are, of course, very much used. But the problem with cycle-level simulators is that, despite the fact that they are extremely accurate, since they are accurate at the cycle level, their simulation times are prohibitively expensive. And in cases such as sparse algebra, where the performance varies a lot depending on the specific input that we provide to the accelerator, testing on smaller inputs may not generalize to the actual workloads that we will have to use on the accelerator. So to address this issue, domain-specific simulators have been introduced. One of these is TEAL, which is a simulator that can only simulate architectures for sparse tensor algebra, but in this specific domain can obtain good enough accuracy while achieving orders of magnitude speed up in terms of actual simulation runtime. Now, that being said, TEAL still is too slow for many practical purposes. And in fact, its execution time on the data set that was used to validate it was of multiple days and required hundreds of gigabytes of RAM. And to address this, we proposed Turquoise, which is a simulator which has the objective of obtaining similar accuracy to TEAL, but with a much higher performance obtained through FPGA acceleration. Now, the way Turquoise works is it accelerates the simulation by generating a prototype of the architecture that we want to model, and then analyzing its execution time. And the way we could do this is we could use one of the existing frameworks or compilers, such as DSAs, Spatial, or Stellar, to generate RTL for the architecture that we want to model. And then we could put this architecture on an FPGA and physically measure its execution time and energy consumption. However, this approach has some problems. First off, it is limited by the amount of resources that we have on the FPGA. So if we want to model a state-of-the-art accelerator that has maybe a 1 gigahertz block, a 3 megabyte cache, and a large number of processing elements, we would need to physically fit that many resources on the FPGA. Another problem is that what we test may not generalize when we change target architecture, for example, from an FPGA to an ASIC. And also the bitstream generation times of these frameworks are often quite long. So they are often not suitable for domain space exploration. And to address this, we propose a different approach, which is instead of generating a copy of the architecture that we want to model, we instead generate still generate a bitstream for the FPGA, but we model a simplified version of the architecture which doesn't require the same size cache, it doesn't require the same number of processing elements or frequency. And then we collect some metadata during execution and measure and compute estimates of the execution time according to some mathematical models. So the overall framework is that we have a CPU, which is the host, which provides the inputs to our simulation. And then the accelerator, the FPGA, contains this model of the architecture, and it's composed of 3 units. One takes care of interaction with the host. Another one takes care of the computation itself. And the last one, the meta-bit extraction, is responsible for extracting the data that we need to then compute metrics such as the simulation, the execution time of the architecture that we are simulating. Now, in particular, we start with the computation unit. And what this does is it performs kind of a functional description of the architecture. It's a little bit more of a functional description because we also consider the iteration order, for example, for in the case of sparse matrix product. Now, the way that Turquoise works in this case is it relies on the model of the sparse abstract machine, or SAM, which is a computational model that maps tensor operations to a set of data flow primitives that can then interact and exchange data through streams. So for example, here we see the SAM model for sparse matrix product, or SPM using the Gustafson algorithm. And there are a set of primitives that are shown in various colors. And these primitives, for example, the level scanner, the array, and the level writer, are used to read and write data to memory and encode it into streams. And then this data is passed to the other primitives, such as the repeater, intersector, and coefficient dropper, which are used for co-iteration and to perform, for example, loops, and then to the multiplier and reducer, which are used for the actual floating point operations. Now, the Turquoise and SAM use a model called a fiber tree, which is an abstraction that allows us to specify a tensor of any number of dimensions with a format that is independent of the actual storage format that we use in memory. And it uses this tree abstraction, like the one we show on the right, where each level of the fiber tree corresponds to a physical dimension. So, for example, the rows of the matrix on the left and the columns. And in each of these levels, we store the coordinates that correspond to a point that corresponds to a non-zero value in the tensor. And then the largest challenge of the work was the fact that SAM is just an abstract model, but doesn't provide any specific implementation for its primitives. And instead, Turquoise has to provide concrete RTL for these primitives. For example, let's consider the reducer, which is the most complex primitive that had to be modeled. So the reducer takes in multiple tensors, one after the other, like the matrices that we see here, and then at the end of execution produces their element-wise sum. And there must be a generalized reducer implementation for each number of physical dimensions of the tensor. So for example, we have a reducer that just reduce single values. We have reducers for vectors, for matrices, and in general for any dimensionality. Now, the problem is that in the state of the art, there was no generalized implementation of a fiber tree reducer. Moreover, there are multiple approaches that we can take for such a primitive. For example, we could use a dense approach, mapping each possible coordinate of the tensors to a physical location in memory. But this, of course, struggles for sparse inputs because we are wasting a lot of memory, and especially when the inputs are very sparse, this may be unfeasible. And we could also use a completely sparse approach where only the coordinates that correspond to non-zero values are mapped to a physical location in memory using techniques such as hashing, but this has a very large overhead in terms of area used for logic. So instead, we use a hybrid approach by splitting the tensor into blocks and then performing the reduction in a dense way within each block. And we do this in an iterative way, where we consider each block one after the other. And at the end of each iteration, we use what is called a tensor unioner, which is a primitive that takes in the partial results that we have obtained and outputs the final output. Now, the last unit of Turquoise's framework is the metadata extraction unit. So this is responsible from actually getting the data that we need for simulations. So the way the simulation works is the computation unit performs a version of the computation that is going on in the architecture that we are modeling, and the metadata extraction unit gets some metadata doing execution. And then this metadata is used to actually compute the metrics that we want. And specifically, I'm going to give you an example of one of these metrics, which is the execution time of the architecture that we're modeling. And we use the same models as Theo. Specifically, we use mathematical models such as the roofline model. So we model the total execution time as the maximum between the time spent for computation and the time spent for memory operations. And then we can retrieve the time spent for computations by computing, doing execution, extracting the number of operations for each type of arithmetic operation, and then knowing the number of processing elements of the architecture and the throughput of each operation. And we can compute the time spent for memory transfers by assuming they happen at the memory bandwidth and computing an estimate of the amount of data transferred with memory during execution. Now, of course, these are simplified assumptions, but TL has shown us that for state-of-the-art DSAs, these provide good estimates of the actual execution times. Now, what is the most complex part of this modeling aspect is cache simulation, because a way that we could simulate a cache of an architecture is we could instantiate that cache on the FPGA and then measure how much data gets transferred to and from the DDR. However, the problem with this is that, as we said, we may not have enough resources on the FPGA to actually have a large enough cache. So instead, what is done is each primitive that interacts with memory instead interacts with an arbiter, which serializes the accesses, and then the accesses are both provided to a memory controller, which provides the data for the execution to the primitives, but also to a separate primitive, which is used to perform the simulation according to a mathematical model. And the simulator can then use different policies for our cache and store all of the required data into the DDR instead of necessarily needing a large cache in the device. Now, moving on to the results, we evaluated Turquoise by modeling two algorithms, which are SPMV, or sparse matrix vector product, and SPM, which is sparse matrix product. And specifically for SPM, we consider Gamma's architecture, which is a state-of-the-art accelerator for the for sparse matrix product using Gustafson's algorithm. We use the same data set that was used to evaluate TL and deploy Turquoise on an AMD value to 550. Now, there are two metrics that we are interested in, which are the accuracy of the simulation, so how correct the results are compared to the actual execution times of the accelerator, and the runtime of the simulation. So we start with the accuracy of the simulation itself, and in this case, the claim was that Turquoise's estimates have a similar accuracy to TL's. And here we see on the left the reported the reported execution times by TL and Turquoise as to the execution time for the different tensors for SPMV. And then on the right, we see the same for SPM. And we also report in the last column the actual execution times of the accelerator. So the goal here, of course, is for the estimates on the execution times to be as close as possible to the actual runtimes of the accelerator. And here we see that for SPMV, Turquoise's estimates are within 1% of TIA's, and actually the only estimate that is different, you don't really see it in this graph, is for the last tensor. And for SPM, we see that the estimates are all within 3.6% of TL's estimates, and we also achieve a lower geomean error than TL. And in fact, on tensors P2 and M, we achieve roughly a 3% lower error than TL. Now, in terms of the performance, here the claim was that Turquoise achieves a much higher performance than TL. And in fact, we have, here I show you the execution times for SPM for the different workloads. And we see, and the workloads are ordered by their size. And we see that the execution times, of course, increase with tensor size, but the speedups also increase, because for the smallest workload, we only have a 7x speedup, and for the largest one, we have over 1000x. And overall, on average, we have a geometric mean speedup of 150x for sparse matrix product, and a 97.6x speedup for SPMV. Now, what I showed you before is the execution runtime, which is what we can call the asymptotical result. Now, of course, you may wonder, well, Turquoise also uses FPGA acceleration, so of course we need to generate a bit stream for the FPGA. Does this additional time counter the speed up that we observe for the simulation itself? And the answer for a large enough data set is no, of course. So for a small data set, like the one we see on the left, where we only test on the smallest workload, Wikibode, we see that Turquoise, accounting for both build and simulation runtime, has a 0.5x speedup, so it performs worse. But as soon as we increase the dataset size, for example, by using the largest tensor, we already have an 11.6x speedup. And when we consider the entire dataset that we use for evaluation, the speedup increases to 15x. And the reason for that is that the bit stream only needs to be generated once and then can be reused for multiple inputs. And not only that, we also observe a speedup for SPMV, which is a much less computationally expensive kernel and in fact, we observe a 3x speed up over TL. Now, the consequence of this much higher performance, which is in fact orders of magnitude higher, is that we can enable a much larger domain-specific exploration, domain space exploration. And for example, here I report an analysis of Gamma's architecture where I changed the size of the cache of the architecture and the policy that is used for eviction, specifically using the FIFO, or first in, first out, and least recently used policies. And I tested 9 different configurations and collected the estimated memory, estimated time required to transfer the data from memory, basically. And this only required the time for one build, which was around 3 hours, plus the execution time, which was in total around 15 minutes. Now, doing the same for TL would have required running on the entire data set 9 times. And considering that running on the entire data set once requires 2 days, doing this 9 times would have required roughly 18 days, which is, of course, unfeasible. Now, to conclude, the Turquoise has shown similar simulation accuracy to TL on both SPMB and SPM, which are the most popular kernels used in sparse tensor algebra. And it decreases the simulation runtime on SPMB from 2 days to just 3.5 hours. Now, the future work is we envision a compiler from SAM's intermediate representation, the one that you saw a few slides ago, to Turquoise to basically improve the usability of the tool. So that was all from me. And if you have any questions, then I would be happy to answer them.
Thanks a lot, Francesco, for the talk. I have actually curiosity. If we have questions from home, from just open the mic or write in the chat. I was curious about the other resources. Like I use more GPUs, so I was like how FPGAs compare, how how is the framework scalable with respect to bigger workloads or.
Okay, so since we evaluated SPMB and SPM, there are 2 different designs on the FPGA that we considered. And the main resources on an FPGA are the flip-flops that are used as registers, basically, the LUTs, which are used for logic, and the BRAMs and URAMs, in this case, which are used for basically local memory. And then we also have DSPs, which aren't really used in this specific case. Now, in terms of the usage of the resources, for both SPMB and Gamma, we have utilization rates that are below 10% for both LUTs and flip-flops. So those are clearly not a problem for scaling. And the most used resource is BRAM, which is around 10% for SPMB, where it is used to store the vector in the matrix vector product, and roughly 20 to 22% in SPM. And in this case, it is used for higher performance in the reducer. Now, 22% is obviously much lower than the total amount of resources that we have. So there is no problem in scaling to larger designs. And if we did need more resources, then these resources that are used for for the reducer could be freed up by simply storing the data in DDR rather than in local memory by decreasing a little bit the performance, which is actually already implemented inside of the tool.
Okay. Another curiosity, if you change like the board, if you go to another or U80, you have to regenerate the bit stream.
Yes.
Because it's a
yes.
different hardware.
You generate the bit stream again, but at least for LVL boards, the process itself doesn't change by much of building itself. You just have to change the target, and then, for example, the U280 has a similar amount of resources. I think it has roughly a little bit less, maybe 20% less, but maybe 20 to 30% less, but still, it easily fits there.
Okay. Good. So if you have other questions from here, from home, we have more time. Okay, otherwise, thanks a lot, Francesco, for the talk.
Thank you for having me.
Thanks everyone for participating. We will see you in the next Friday talk next week with Professor Maggioni from Politecnico di Milano. So thanks again. Have a good day.